Welcome to Mechanics of Rest. There is a question that sounds almost too simple at first. What sits directly above and below the sun? On Earth, above and below feel obvious. The ground pulls one way, the sky opens the other, and every map quietly agrees with the body. But around the sun, there is no floor, no ceiling, and no natural direction waiting to be found. The moment the question is taken seriously, it begins to change. Above what plane? Below which axis? North by whose measurement? South according to what map? And beyond the geometry, the answer becomes stranger. The regions above and below the sun are not empty corners of space. They are shaped by solar poles, magnetic fields, coronal holes, fast streams of charged particles, and spacecraft that had to leave the flat plane of the planets to discover what was really there. Before we begin, if you enjoy long form science and history told in this slower documentary style, a like and subscription helps Mechanics of Rest keep making these full stories every week. And let us know in the comments where you are listening from tonight. If there is a person, topic, story, scientific mystery, or historical era you would like us to cover next, leave that as well. For now, the question begins not with the sun itself, but with the words we use to locate anything around it. Chapter 1: The Problem of Above. On Earth, above and below seem to belong to reality before anyone explains them. A stone leaves the hand and falls downward. Rain comes from overhead. Smoke rises from a fire. Dust settles onto a floor, and the body learns direction long before it learns language. The words feel simple because gravity gives them weight. Down is where things go when nothing holds them. Up is the direction a person lifts the eyes when the ground is no longer enough. This ordinary certainty is so familiar that it follows human thought into places where it no longer fits. People speak of the top of a map, the bottom of a page, the upper sky, the lower ground, the northern half of the world, the southern half of the world, as if direction were built into the universe in the same way it is built into standing on a planet. For daily life, this is harmless. A person has to walk, build, climb, lie down, point, and return home. But the moment the question moves away from Earth and toward the sun, the words begin to loosen. Around the sun, there is no ground under the solar system. There is no roof above it. A spacecraft passing near the sun does not cross an invisible ceiling when it moves in one direction, or descend toward a cosmic basement when it moves in another. It follows a path shaped by speed, gravity, and the pull of the bodies around it. Its instruments measure particles, magnetic fields, light, and motion. The words above and below can still be used, but only after someone has said what they are measured from. That is what makes the question so quietly strange. What sits directly above and below the sun sounds, at first, like a question about objects. It seems to ask whether there is a planet, a cloud, a hidden belt of matter, or some unmapped region suspended over the star and mirrored beneath it. But before any object can be named, the direction itself has to be chosen. Above which plane? Below which axis? North according to which rotation? South according to which coordinate system? The first answer is not a thing in space. The first answer is a map. Ancient astronomy could not begin anywhere except from Earth. The eye looked upward from the ground, and the sky appeared to turn overhead with a regularity that seemed to confirm Earth's central position. Claudius Ptolemy's system, developed in the 2nd century, placed Earth near the center of the celestial arrangement and described the wandering planets through careful mathematical devices. It was not a foolish system. It preserved observed motions with remarkable discipline for its time, using circles upon circles to account for what the eye could see. But its deepest orientation came from the human position on a surface. From that surface, the heavens naturally seemed arranged above. The moon was above Earth. The planets were above Earth. The fixed stars were farther above still. This was not only a scientific claim in the old sense, it was also a bodily experience. The sky was what lay overhead, and the ground was what lay below the feet. A whole universe could be organized around that feeling, especially before instruments revealed how much the feeling concealed. Nicholas Copernicus disturbed that arrangement in the 16th century by placing the sun near the center of planetary motion. The change is often described as a shift in cosmic importance, with Earth moved away from the middle of things. But it was also a shift in direction. Earth was no longer the stable platform from which the universe received its natural up and down. It became one moving body among others, circling the sun while carrying its own local horizon with it. A person standing in a field still knew which way a stone would fall, but astronomy could no longer treat that local downward pull as the organizing principle of the heavens. Once Earth became a planet, direction had to become more formal. Astronomers needed reference planes, axes, angles, and coordinates. These tools may sound dry, but they are what allow space to become describable. A coordinate system is an agreement about how to locate something. It does not make one direction sacred. It does not declare one side of space higher in any absolute sense. It creates a shared language so that an observer in one place and an observer somewhere else can describe the same object without depending on the ground beneath either of them. On Earth, the idea is already familiar. Latitude measures distance north or south of the equator. Longitude measures position east or west from an agreed meridian. No visible lines are carved into the oceans, and no glowing belt wraps around the planet at 0 degrees latitude, but the system works because the rotating Earth gives it a natural structure. The equator is tied to the planet's spin. The poles are tied to the ends of its axis. A city, a mountain, a ship, or a storm can be placed inside that framework, and the framework remains steady enough to be useful. The sun can also be mapped in a similar way, though the task is more delicate. It rotates, and so it has an axis. It has an equator lying halfway between the two ends of that axis. It has northern and southern solar latitudes, used to describe where features appear on its surface and in its atmosphere. These are not decorations added to a picture of the sun. They are working tools. Without them, the movement of sunspots, the drift of magnetic regions, the development of coronal holes, and the path of spacecraft around the sun would be much harder to describe. Yet the sun is not a solid globe like Earth. It is a star made of plasma, and plasma does not rotate as a rigid shell. Near the solar equator, the surface turns at one rate. At higher latitudes, it turns more slowly. This differential rotation matters because the sun's magnetic field is carried and twisted by the moving plasma. Even the act of defining solar direction leads into physical behavior. Solar north and solar south are not only labels on a diagram, they point toward regions where rotation, magnetism, and outward flowing particles take on forms that differ from what happens nearer the equator. Another reference plane is even more common in discussions of the solar system. This is the ecliptic plane, the plane of Earth's orbit around the Sun extended outward into space. Because Earth's path gives observers a stable and measurable surface, the ecliptic became one of astronomy's most useful frames. In a diagram, it often appears as the flat sheet on which the planets move around the Sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune do not all follow exactly the same plane, but most of their orbits stay close enough to it that the solar system looks broadly flattened. The flatness is real, but it is not absolute. Pluto's orbit is tilted more strongly than those of the major planets. Many comets come in at steep angles, arriving from paths that do not respect the neat planetary sheet. Asteroids, dust, small bodies, and spacecraft all have their own inclinations. The solar system is not a thin drawing. It is a three-dimensional arrangement with a preferred plane, and that plane matters because it shapes how human beings have explored it. Most spacecraft have traveled near it. Most planetary motion is described relative to it. Most views of the sun have been taken from close to it. If above means above the ecliptic, then one answer begins to appear. Above the sun lies the half of space north of that orbital plane. Below the sun lies the half south of it. But those halves are not separate rooms. They are regions of interplanetary space containing fields, dust, particles, and the outward influence of the sun itself. A spacecraft moving above the ecliptic would not pass into some new layer of the universe. It would pass into a different latitude of the same solar environment, where the sun's wind and magnetic structure may look different from what is measured near the planetary plane. If above means above the sun's own equator, the answer shifts. Now the question points toward the solar North Pole and the space extending outward from it. Below points toward the solar South Pole and the space beyond that region. This distinction matters because the sun's equator is not perfectly aligned with the ecliptic. The solar rotation axis is tilted by a little more than 7 degrees relative to Earth's orbital plane. It is a small angle in ordinary terms, but in solar observation it has large consequences. It means Earth never looks straight down onto the sun's poles. During the year, Earth sees the sun from slightly changing angles. At one part of the year, the northern solar pole is tipped a little more toward Earth. At another, the southern pole is favored, but the improvement is modest. The view remains shallow. From near the ecliptic, the sun's poles sit close to the visible edge of the solar disk, where perspective compresses surface features. The problem is not that the poles are too distant. The whole sun is distant. The problem is that they are seen from the wrong angle. A round object viewed from the side teaches this without needing a formula. Markings near the center of the visible face appear broad and clear. Markings near the edge seem narrowed, crowded, and bent around the curve. Nothing about the object has changed. Only the viewing angle has changed. The same difficulty affects solar observation. A magnetic feature near the solar equator can be tracked across the disk with greater ease. A feature near the pole is pressed toward the limb, where its shape and field direction are harder to measure. For a long time, this meant that the sun's polar regions were known partly through inference. Observatories could see signs of them. Instruments could measure light, magnetic fields, and motion from the available angle. Solar physicists could build models, compare data, and follow the changing cycle. But the direct view was limited by the same geometry that keeps most planetary exploration near the ecliptic. Humanity had watched the sun for centuries before it found a practical way to leave the flatness of its usual viewpoint. The phrase directly above the sun therefore begins to hold several answers at once. Directly above the ecliptic, there is interplanetary space shaped by the sun's gravity and filled by the solar wind. Directly above the solar North Pole, there are polar magnetic fields, high latitude corona, and regions where open magnetic structures can guide charged particles outward. Directly below the solar South Pole, similar processes unfold with their own timing and polarity. The answer is not a single hidden object. It is a layered environment. This environment is not empty in the ordinary sense. Space near the sun contains plasma, the thin flow of charged particles that streams outward from the solar atmosphere. It contains magnetic fields carried through space by that flow. It contains dust, energetic particles, and the faint structures of the heliosphere, the immense region inflated by the sun into interstellar surroundings. Above and below the sun, in a physical sense, lie parts of that same solar domain, shaped differently depending on latitude, magnetic cycle, and distance. The poles are especially important because the sun's magnetic field changes over time. During the solar cycle, magnetic activity rises and falls. Sunspots become more numerous and then fade. Magnetic polarity reverses. Coronal structures reorganize. The polar regions help scientists understand how one cycle gives way to another because the polar fields are connected to the large-scale magnetic pattern that the sun carries into space. A place that appears quiet at the edge of an image can hold information about the future behavior of the whole star. This is one reason the question is more than a curiosity. What lies above and below the sun touches the geometry of the solar system, the rotation of the star, the behavior of plasma, the structure of magnetic fields, and the limits of human observation. It asks why most views of the sun have come from one broad belt of space. It asks what changes when a spacecraft tilts away from that belt. It asks whether nearness to the sun is enough, or whether angle matters just as much as distance. The early answer, then, is not that something simple sits above the sun like an object placed on a shelf. The early answer is that above and below must be earned by definition. Around the sun, direction begins with a plane, an axis, and a decision about the map being used. Once that decision is made, the question opens into real places and processes. The solar poles, the high latitude corona, the fast solar wind, the magnetic fields reaching outward, and the spacecraft sent to measure what ordinary earthbound viewing could not. For most of human history, the sun was watched from almost the same broad level as the planets. The view was familiar, productive, and incomplete. The next step is to understand that level itself, the wide orbital plane that quietly shaped almost every early answer humans gave about the solar system. Before the sun's poles can be understood as regions above and below, the plane around the sun has to come into view. Chapter 2: The Plane Around the Sun. Before the sun can have an above or a below, the solar system needs a surface that can be used as a beginning, not a real surface, because no hard sheet runs through the planets. Nothing in space marks the line with dusted chalk or a thin shining edge. The surface is mathematical, but it is not imaginary in the careless sense. It comes from motion. It comes from the path Earth follows around the sun, and from the fact that most of the major planets travel near that same broad level. This surface is called the ecliptic plane. The name comes from the apparent path the sun seems to follow through the sky over the course of a year, as seen from Earth. Long before modern spacecraft, long before cameras watched the sun from orbit, the ecliptic was a practical fact for sky watchers. The moon and planets appeared near a narrow band of the heavens. Eclipses occurred only when the moon crossed that band at the right time. The sky, when watched carefully over months and years, seemed to carry a hidden road. In modern terms, the ecliptic is the plane of Earth's orbit around the sun. If Earth's yearly path were traced as a ring, and that ring were flattened into an endless reference sheet, the ecliptic plane would be the result. Astronomers use it because Earth is the observing platform from which much of astronomy began, and because Earth's orbit provides a stable and measurable frame. It is not the only possible plane. It is not the universe's floor, but it is one of the main surfaces from which direction inside the solar system has been described. Most of the major planets keep close to this plane. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune move around the sun in paths that are tilted only modestly relative to one another, with Mercury's orbit being the most noticeably inclined among the major planets. This shared flatness is not an accident. The solar system formed from a rotating disk of gas and dust around the young sun. As that material settled, collided, accumulated, and formed larger bodies, much of the motion remained organized around the same original spin. A rotating disk is one of nature's efficient ways of arranging matter around a center. Material with different motions meets, loses some of its disorder through collisions and interactions, and gradually shares a common plane. The planets are the large surviving bodies from that early history. Their present orbits still preserve the memory of the disk from which they formed, though not perfectly. The solar system is not a clean drawing with every orbit pressed onto one line. It is flatter than a random swarm, but thicker than a diagram. Johannes Kepler helped turn planetary motion from an inherited celestial pattern into a measurable geometry. Working with Tycho Brahe's observations of Mars, Kepler found that planets moved in ellipses rather than perfect circles. This was a patient and difficult change. Mars did not fit comfortably into the older circular expectations, and Kepler's work forced the motion itself to become the guide. By 1609, in Astronomia Nova, he had published the first two of the laws that would make planetary orbits into a new kind of mathematical landscape. Kepler's discovery did not by itself create the ecliptic plane, but it clarified the kind of order to which such planes belonged. Planets were not fastened to crystal spheres. They followed paths in space, and those paths could be measured. Each orbit had a shape, a tilt, and a relation to the Sun. Once planetary motion became something like this, the solar system could be described less as a stack of heavenly layers and more as a family of inclined tracks around a common star. The ecliptic became the most familiar of those tracks because Earth's orbit gives human observers their yearly frame. From Earth, the Sun appears to move against the background stars along the ecliptic, passing through the constellations of the zodiac. This apparent motion is really Earth's motion translated into sky language. As Earth changes position around the Sun seems to appear in different directions against distant stars. The effect is a reminder that even a simple sky path can be the shadow of a deeper orbital fact. For the question of above and below the Sun, the ecliptic is tempting because it gives the solar system something like a middle surface. Above the ecliptic lies one half of nearby solar space. Below it lies the other. Spacecraft can be described as north or south of that plane. Comets can enter at high inclinations. Dust can occupy broad clouds around it. The planets themselves, even when slightly tilted, move close enough to the ecliptic that it becomes the default flatness of the planetary system. But the default is not the same as the whole. Pluto's orbit, though Pluto is now classified as a dwarf planet, is tilted much more steeply than the orbits of the major planets. Many long-period comets arrive from directions far outside the planetary plane, some moving on paths that seem almost indifferent to the familiar arrangement of the planets. Certain spacecraft also leave the ecliptic by design or by gravitational assistance. These high-inclination paths reveal a solar system that is flatter than a sphere, but not confined to a single surface. A thin layer of dust also follows the inner solar system, producing what observers on Earth call zodiacal light under dark conditions. This dust is spread through the region where the planets move, scattering sunlight along the ecliptic. It is not a wall, not a border, and not an answer to what lies above the Sun, but it shows how the plane can become physically populated. The reference sheet used by astronomers also corresponds to a region where matter has actually gathered over time. Still, the ecliptic is not the Sun's own equator. That difference is easy to miss because diagrams often place the Sun upright at the center, with the planets circling neatly around its middle. Reality is less aligned. The Sun's rotation axis is tilted by a little more than 7 degrees relative to the ecliptic plane. This means the Sun's equator is not exactly the same as the plane in which Earth travels. Solar north and ecliptic north point in nearly the same general direction, but not precisely. 7 degrees may sound small, almost too small to matter. In the geometry of observation, it matters constantly. From Earth, that tilt allows one solar pole to lean slightly toward us at one part of the year, and the other pole to lean slightly toward us 6 months later. The effect gives solar observers some seasonal change in polar visibility, but never a direct overhead view. Earth remains near the ecliptic. Its path does not climb far enough above or below the Sun's equator to look down cleanly onto either pole. This is one of the quiet reasons the sun's poles remain difficult. Better telescopes could sharpen the image, and modern instruments could measure light in wavelengths no human eye can see. They could reveal hot plasma, magnetic regions, loops, holes, flares, and sunspots with a detail earlier observers could not have approached. Yet the basic viewing angle remained constrained. A camera can be excellent and still be placed in the wrong seat for a certain question. The ecliptic also shaped the practical roots of spacecraft. Reaching space is already expensive in energy, and changing the tilt of an orbit around the sun requires additional energy. Most missions naturally remain close to the plane in which Earth itself moves because they begin from Earth and inherit much of Earth's orbital motion. To leave that plane meaningfully is not like steering upward with an ordinary engine. It demands careful mission design, gravity assists, and patience. This is why high latitude solar observation became a special achievement rather than an early convenience. A spacecraft can travel closer to the sun while still remaining near the ecliptic. It can endure heat, sample plasma, and watch the corona without seeing the poles from above. Closeness answers one set of questions. Inclination answers another. The sun does not reveal its three-dimensional structure only to the spacecraft that approaches nearest. It reveals different things to the spacecraft that changes angle. The ecliptic plane, then, is both helpful and limiting. It gives the solar system a usable orientation. It explains why the planets appear organized rather than scattered in every direction. It provides the reference from which astronomers can say that an object lies above or below the broad planetary level. But it also hides how much depends on perspective. A plane that makes maps easier can make a star look flatter than it is. Above the ecliptic, there is no separate kingdom of space. Below it, there is no mirrored lower world. There are extensions of the same solar environment, solar wind, magnetic fields, dust, particles, and the long reach of gravity. What changes is the angle at which the sun's influence is crossed and measured. Near the ecliptic, spacecraft pass through regions shaped by equatorial solar conditions and by the broad structure of the planetary system. Farther above or below, the influence of the polar regions becomes more direct. This distinction prepares the deeper answer. If the question is only about the ecliptic, then above and below the sun describe position relative to the planetary plane. But if the question turns toward the sun itself, the ecliptic is no longer enough. The sun has its own equator, its own rotation axis, and its own poles. To understand what lies directly above and below the sun in the solar sense, the next step is to leave the planetary sheet behind for a moment and look for where solar north begins. Chapter 3: Where the Solar North Begins. Solar north begins with rotation. The sun turns, and because it turns, it has an axis. That axis cannot be seen as a rod passing through the star, and no physical line runs from one solar pole to the other. It is a direction inferred from motion. Features on the sun move across the visible disk, disappear around one side, and return after the star has turned enough to bring them back into view. From that repeated motion, astronomers can define the broad middle of the sun, the ends of its rotation, and the latitudes between them. A solid planet makes this easier to picture. Earth has continents, oceans, mountains, and ice sheets that rotate together with the body beneath them. Its axis can be tied to the turning of the whole globe, and its poles become fixed geographic places. The Sun is different. Its visible surface is not a hard shell, but a layer of hot plasma, and different latitudes rotate at different rates. The equator turns faster than regions closer to the poles. A point at one latitude does not keep perfect pace with a point at another. Solar north, therefore, belongs to a rotating plasma body, not to a rigid ball. That difference is one reason the Sun had to be studied patiently before its own geography could become useful. From Earth, the Sun appears as a bright disk, and for long stretches of history it could not be examined directly without danger to the eyes or damage to instruments. Early solar observers relied on projection, filtered viewing, drawings, and repeated comparison. They watched markings on the disk not as decorations, but as clues. A dark spot appearing near one edge, crossing over days, and approaching the other edge gave evidence that the sun itself was turning. Richard Carrington became one of the important 19th century observers who gave that turning sun a more precise frame. In the 1850s, he carefully recorded sunspot positions day after day, building a disciplined record of where spots appeared and how they moved. His work belonged to a period when solar observation was becoming more systematic, with drawings, timing, and positional measurement replacing the looser reports of earlier sky watchers. He was not only looking at dark marks, he was using them as tracers of rotation. Carrington's observations helped define what is still called Carrington rotation, a solar rotation period used as a reference for mapping the sun over time. As seen from Earth, one Carrington rotation is about 27 days. The number is not the same as the sun's true rotation period in an absolute sense, because Earth is also moving around the sun while observations are being made. Still, it gave solar physicists a practical clock. A feature could be followed, a map could be updated, and the changing surface of the sun could be placed into a repeated frame. Sunspots themselves made this work possible because they are visible signs of magnetic activity. They appear darker than their surroundings because they are cooler than the bright photosphere around them, though still extremely hot by ordinary standards. Their darkness is relative. A sunspot removed from the sun and seen against a dark background would be intensely bright. On the solar disk, it appears dark because the surrounding surface is brighter. This small visual contrast became a doorway into the sun's deeper magnetic behavior. Through such spots, observers learned that the sun does not rotate like Earth. At the equator, the solar surface completes a rotation in about 25 days. At higher latitudes, the rotation takes longer, reaching roughly 30 days or more near the polar regions, depending on how the measurement is made. This differential rotation is not an error in observation. It is a property of the sun's plasma. The material is hot, ionized, and mobile, and the star's outer layers can shear past one another in ways a solid crust cannot. The rotation has a rhythm without making a sound. Across the solar disk, spots appear, advance, alter their shapes, and vanish around the limb. New regions form while old ones decay. Bright areas and dark areas do not sit on a painted sphere. They belong to a surface that is continually renewed from below and shaped by magnetism. The sun turns as one body, but not as one rigid piece, and the difference between those two facts lies at the root of its activity. Solar north and solar south are defined through this turning. The North Pole lies at one end of the rotation axis, the South Pole at the other. Between them lies the solar equator, and from that equator, astronomers measure heliographic latitude. A sunspot group may be described as appearing in the northern solar hemisphere or southern solar hemisphere. A coronal hole may develop near a pole. A spacecraft may pass through a high solar latitude. These phrases depend on the axis first established by rotation. Heliographic coordinates make the sun mappable, even while the sun refuses to behave like a stable map. Longitude on the sun is more complicated than longitude on Earth because the surface rotates differentially and features change over time. A sunspot is not a city. A magnetic region is not a mountain. It can form, split, fade, or be carried by plasma motion. Still, a coordinate frame allows scientists to say where something was, how it moved, and how its position related to the larger solar cycle. Carrington's name remains attached to this mapping because his system gave solar observers a way to count rotations and assign longitudes in a practical way. The Carrington coordinate system rotates at a fixed rate chosen to match the motion of sunspots at certain latitudes, especially those where sunspots commonly appear. It is an approximation, but a useful one. It allows one observer's record to be compared with another's, and it lets modern instruments connect changing solar features across time. The need for such approximations reveals something important about the Sun. A planet's geography can be drawn once and then corrected as better measurements arrive. The Sun's geography is partly a geography of motion. Its latitudes matter because they rotate differently. Its poles matter because they are tied to large-scale magnetic fields. Its equator matters because much of the visible sunspot activity emerges in belts that shift over the course of the solar cycle. Position on the sun is never only position. It is also timing, magnetic state, and motion. This is why the idea of solar north cannot be separated from the solar cycle. Sunspots do not appear randomly across all latitudes. During a typical cycle, they tend to emerge first at mid-latitudes and then appear closer to the equator as the cycle progresses. When plotted over time, their latitudes form the famous butterfly diagram, named for the shape made by the spreading and narrowing wings of activity in the northern and southern hemispheres. The diagram turns solar latitude into a record of time. That pattern shows that the sun's north and south are active hemispheres with their own behavior. The two sides are related but not perfectly identical. One hemisphere can be more active than the other for a period. Sunspot numbers, magnetic regions, and eruptions can show asymmetries between north and south. The sun is one star, but its activity does not always distribute itself evenly. Above the solar equator, the magnetic surface has a history. Near the poles, the story becomes harder to see. Sunspots usually do not dominate the polar caps in the same way they appear at lower latitudes. The poles can seem quieter in ordinary visible light, especially when compared with active belts crowded with sunspot groups. But quiet appearance should not be mistaken for scientific emptiness. The polar regions carry magnetic fields that help shape the solar cycle, and their structure influences the high latitude solar wind. They are difficult not because nothing happens there, but because the important processes are not always arranged for easy viewing from Earth. A pole is also not a point in the everyday sense. On a map of Earth, the North Pole can be marked by a precise coordinate, 90 degrees north. On the Sun, the mathematical pole is a direction on a rotating sphere, but the surrounding polar region is the important physical area. It includes high latitudes where magnetic fields, coronal holes, and plasma flows become part of the larger solar environment. When someone asks what sits above the sun, the answer is not balanced on a dot at the top of the star. It extends outward from a region. From the solar North Pole, magnetic structures can open into space. From the solar South Pole, related structures can do the same, though their polarity and configuration change with the solar cycle. These open fields are connected to streams of charged particles that leave the sun and move through the heliosphere. The poles are therefore gateways in a magnetic sense, though not openings in a surface. They are places where the sun's field can connect the star's outer atmosphere to interplanetary space. The word gateway can mislead if taken too literally, so the physical picture has to remain grounded. The sun has no solid crust with doors. Its atmosphere thins outward through layers: photosphere, chromosphere, corona, and then the solar wind that continues into space. Magnetic field lines provide structure to this plasma. In some regions, loops close back toward the sun. In others, fields extend outward, and the plasma follows paths that carry it away. Near the poles, especially during certain phases of the solar cycle, large open field regions can dominate. This makes solar north a practical direction for spacecraft and instruments. A mission that climbs to high solar latitude can measure conditions that are not the same as those near the ecliptic. It can sample the solar wind coming from polar regions. It can help determine how the magnetic field is organized above and below the solar equator. It can test whether models built from side-on views of the sun are missing crucial parts of the structure. Direction becomes experiment. The difficulty is that Earth-based observers begin from a poor angle for this specific task. Earth stays close to the ecliptic plane, and the ecliptic is tilted only modestly relative to the sun's equator. Even when the sun's north or south pole tips slightly toward Earth during the year, the view is still oblique. Details are compressed near the limb. Magnetic measurements become harder because the field is being viewed from the side rather than along a cleaner line. The pole is present, but its full shape is withheld by geometry. For centuries, this geometry defined the limits of solar north and south. Astronomers could measure rotation. They could define the equator. They could map sunspots, trace activity belts, and infer polar fields from available data. They could watch the surface turn through Carrington rotations and build a solar language of latitude and longitude. Yet the regions that gave the axis its ends remained among the least directly seen parts of the star. The phrase above the sun has now changed meaning. It no longer points vaguely upward from Earth's sky. It points toward high solar latitudes, toward the regions around the rotation axis, and toward the space into which polar magnetic structures extend. Below the sun points in the opposite solar direction toward the southern pole and its own high latitude environment. These are not mystical locations. They are technical, measurable, physically active parts of the sun's surroundings. Once solar north has been defined, the original question becomes more exact. Above the sun means above the solar equator or above the ecliptic, depending on the chosen frame. If the frame is the sun's own rotation, then directly above and below lead toward the poles. But defining the poles is not the same as seeing them clearly. The next difficulty lies in the angle of observation, because for a long time the sun's polar regions were always present in the data and always partly hidden by the way human observers had to look. Chapter 4: The Poles We Could Barely See. For most of the history of solar observation, the sun was watched from almost the same broad level. Earth moves around the sun close to the ecliptic plane, and nearly every telescope on Earth inherits that position. Even when instruments became sharper, even when glass improved, even when photography replaced hand drawing, the basic viewing angle remained stubbornly familiar. The sun could be studied in more detail, but still mostly from the side of its rotating body. This is easy to miss because the sun seems so fully visible. It rises as a disk, sets as a disk, and in filtered images it appears round, complete, and available. A photograph of the sun can give the impression that the whole star has been presented at once. But a sphere does not reveal all its regions equally from one direction. The middle of the disk faces the observer more directly. The edges curve away. Near those edges, the same surface area is squeezed into less apparent space, and features become harder to interpret. The poles sit inside this problem. From Earth, the sun's north and south polar regions are not hidden behind the star, but they are rarely seen from a favorable angle. They lie near the upper and lower edges of the visible disk, depending on the season and the sun's slight tilt toward Earth. A feature near the equator may cross the face of the sun with a path that can be followed clearly for days. A feature near a pole is pressed toward the limb, where distance across the curved surface becomes harder to judge. The technical word for part of this difficulty is foreshortening. A shape seen at an angle appears compressed along the line of sight. On the sun, foreshortening affects measurements of size, position, motion, and magnetic field. The polar regions are not only far away in the ordinary sense that the whole sun is far away, they are geometrically inconvenient. Their light reaches Earth, but it carries information from a surface tilted away from the observer. Solar physicists learn to work around this inconvenience with care. Images can be corrected. Measurements can be modeled. Repeated observations across many days can build a fuller picture than a single image allows. But correction is not the same as direct vision. A side-on view can be improved, interpreted, and compared with theory, yet it still leaves certain uncertainties. This is especially true for magnetic fields, because measuring the direction and strength of a field depends strongly on the line from the observer to the solar surface. The sun's magnetic field is often measured through the effect it has on light. Instruments detect subtle changes in spectral lines, especially through polarization, and from those changes, scientists infer magnetic strength and direction. Near the center of the solar disk, the geometry is more favorable for certain measurements. Near the poles, the line of sight cuts across the surface at a shallow angle. The field may be present, but the measurement has to pass through projection effects before it becomes a reliable map. This matters because the poles are not marginal decorations on the sun. They are connected to the large-scale magnetic field that threads through the corona and out into the solar wind. During parts of the solar cycle, polar coronal holes can dominate high-latitude regions. Polar magnetic fields help scientists understand the progress of the cycle and may offer clues about the strength of future activity. A poor view of the poles means an incomplete view of the Sun's global magnetic structure. Ground-based solar observatories gave the first long tradition of disciplined watching, but Earth's atmosphere added another layer of difficulty. Air blurs, scatters, absorbs, and shifts light. Atmospheric turbulence can soften fine detail. Certain wavelengths never reach the ground in useful form. Observers learn to build special solar telescopes, choose mountain sites, use filters, and later employ adaptive optics, but the atmosphere remained part of the observing path. To watch the sun without that layer, instruments had to go into space. Space-based solar observation changed the scale of what could be seen. The Solar and Heliospheric Observatory, known as SOHO, was launched in 1995 as a joint mission of the European Space Agency and NASA. Positioned near the Earth-Sun L1 point, it could keep a steady watch on the Sun without Earth repeatedly blocking its view. SOHO observed the corona, solar wind, oscillations inside the Sun, and many other features across years of changing solar activity. It became one of the great long-duration witnesses of the modern Sun. Yet SOHO's position near Earth also meant that its perspective remained close to the ecliptic. It watched continuously, but from the familiar belt of space where Earth itself travels. The mission expanded what could be measured, not the basic latitude from which the star was seen. For many questions, that was enough. For the poles, it still left the same geometric problem, though now with better instruments and a longer record. The Solar Dynamics Observatory, launched in 2010, brought another level of detail. Its atmospheric imaging assembly watched the sun in multiple extreme ultraviolet wavelengths, revealing plasma at different temperatures in the solar atmosphere. Its helioseismic and magnetic imager measured oscillations and magnetic fields. The images it returned made the sun seem almost continuously alive with loops, active regions, dark coronal holes, bright structures, and slow reorganizations. But SDO, like SOHO, observed from near Earth. Its eyes were powerful, but its seat was still near the old plane. Hinode, launched by Japan in 2006 with international collaboration, added high-resolution observations of the solar atmosphere and magnetic fields. Its instruments studied the photosphere, chromosphere, and corona with a precision that helped connect surface magnetism to structures above it. Hinode could examine magnetic activity with remarkable care. Even so, it too shared the broader limitation of near-ecliptic observation. The polar regions remained seen from the side, refined by better data, but not transformed into an overhead view. A pattern begins to appear across these missions. Better instruments made the sun more detailed. Longer missions made the sun more continuous. Different wavelengths made invisible structures visible. Magnetographs turned subtle properties of light into maps of field strength. Helioseismology used the sun's surface motions to infer processes below the visible surface. Each advance opened a different part of the star, but the polar viewpoint itself required a change in orbit, not only a change in instrument. The difference is like studying a globe placed on a table while always keeping one's eyes near the table's edge. A person may use a magnifying glass, a camera, a lamp, or a ruler, and each tool may reveal more about the globe's surface. But the top remains difficult until the observer changes height. The sun's polar regions posed a scientific version of that problem, with the added complication that the globe was not solid. The markings changed, and the field being measured extended outward into space. Near the poles, the corona can look different from the brighter active regions nearer the equator. Coronal holes may appear as darker areas in extreme ultraviolet or X-ray images because the plasma there is less dense and cooler relative to surrounding coronal structures in those wavelengths. These holes are associated with open magnetic fields, regions where the field extends outward rather than closing back in loops near the sun. During solar minimum, large polar coronal holes can persist, linking the polar regions to streams of fast solar wind. From a shallow viewing angle, such regions can still be detected. Their shape, extension, magnetic setting, and relationship to the pole are harder to determine precisely. The pole may be part of the structure, but it lies close to the edge of the visible disk. A boundary may be real or partly an effect of projection. A magnetic measurement may require assumptions to separate the field's true direction from how it appears along the line of sight. Every observation carries the question of angle inside it. This is where the phrase barely see should be understood carefully. The poles were not invisible. They were observed, monitored, inferred, modeled, and included in solar science. But they were barely seen in the sense that a landscape viewed from the horizon is barely seen. Its outline exists. Its light arrives. Some features stand out. Others overlap, flatten, or disappear into perspective. The missing thing is not attention. The missing thing is position. Position is often the quietest part of discovery. A new instrument can feel more dramatic because it has a name, a launch date, and a list of capabilities. But sometimes the decisive change is where the instrument goes. The same star seen from a slightly different latitude can begin to answer a question that sharper images from the old latitude could not settle. For the sun, the route above and below the usual plane became as important as the camera pointed back toward it. To leave the ecliptic in a meaningful way is difficult because spacecraft launched from Earth inherit Earth's motion around the sun. Earth already travels at nearly 30 kilometers per second along its orbit. A spacecraft departing Earth begins with that sideways motion, and changing the tilt of its solar orbit requires energy. Raising orbital inclination is not the same as pointing a rocket upward from a launch pad. It is a problem in heliocentric mechanics, where speed, direction, gravity assists, and mission timing all have to be arranged. This is why early solar spacecraft mostly remained near the plane where Earth moves. They could go inward toward the sun, outward from Earth or into useful positions near gravitational balance points, but climbing far above or below the ecliptic demanded special design. The solar poles were therefore not neglected because they were uninteresting. They were neglected by geometry, energy, and opportunity. They lay in a direction that was easy to name and hard to reach. The situation also shaped public imagination. The sun was often pictured from the same familiar angle, a round face with features distributed across it. Active regions appeared as bright and dark markings. Flares and loops seemed to decorate the visible disk or its edge. The poles, when included, were often just the upper and lower margins of the image. A flat picture trained the mind to think of the sun as a face, not as a sphere whose unseen latitudes mattered. Scientific models had to do better than the picture. They included magnetic fields extending from polar regions, flows on the solar surface, transport of magnetic flux toward the poles, and the reversal of polarity during the solar cycle. They drew on indirect measurements and mathematical reconstruction. The models were not guesses in the loose sense. They were disciplined attempts to recover a three-dimensional system from limited lines of sight. But every model benefits when a new viewpoint tests it. A more direct polar view promised several gains at once. It could improve measurements of the polar magnetic field. It could show how coronal holes are shaped near the poles rather than only how they appear from the side. It could connect solar surface structures to the high-latitude solar wind measured away from the sun. It could reveal whether the north and south behaved symmetrically or carried differences that side-on observation had softened. Such knowledge matters for the solar cycle, for heliospheric structure, and for space weather forecasting near Earth. The irony is gentle but important. Humanity's star, the object that lights every day, has had regions that were less directly known than many people might expect. The difficulty did not come from distance alone. It came from being trapped, observationally, near the same plane in which Earth travels. Seeing often feels like a matter of looking harder, but in heliophysics it can be a matter of looking from somewhere else. The search for what lies above and below the sun therefore required more than naming solar north and solar south. It required a route. Instruments near Earth had already shown that the poles were magnetic and consequential. Long records from SOHO, SDO, Hinode, and other observatories had strengthened the need for polar knowledge. The next movement belonged to spacecraft that would not merely watch the sun from the old level, but would begin to climb away from it. Chapter 5: Ulysses Above the Solar System. Ulysses entered the story of the sun by refusing the usual plane. Most spacecraft that leave Earth continue, in one way or another, inside the broad level of Earth's motion around the sun. They may move inward or outward. They may travel to another planet, remain near Earth, or settle into a useful observing position. But they usually keep much of the sideways motion that Earth already has. The solar system gives them an inherited path, and that path lies close to the ecliptic. To move above and below the sun in a more serious way, a spacecraft needed to change that inheritance. It had to leave the planetary sheet, not just travel across it. This was a different kind of ambition from flying close to the sun, because the problem was not only distance, it was inclination. The spacecraft had to tilt its orbit so that it would pass over the Sun's high northern and southern latitudes, reaching regions that Earth based observatories could not view directly, and earlier spacecraft had not sampled in the same way. The mission that did this was Ulysses, a joint project of the European Space Agency and NASA. It was launched in October 1990 from the Space Shuttle Discovery, sent first toward Jupiter rather than directly over the Sun. That path may seem indirect, but it carried the logic of orbital mechanics. A spacecraft leaving Earth did not have the fuel to tilt itself steeply out of the ecliptic by engine power alone. Jupiter's gravity could do what fuel could not do cheaply. The giant planet could bend the spacecraft's path. Jupiter was not the destination in the ordinary sense. It was the turning point. Ulysses approached the planet in February 1992, using the encounter to swing into a high inclination solar orbit. After that gravity assist, the spacecraft no longer belonged to the usual flatness of planetary travel. Its path carried it far above and below the Sun's equator, allowing it to pass over the polar regions of the heliosphere. The mission became one of the first true explorations of the Sun's high-latitude environment. There is a quiet elegance in that route. To study the Sun's poles, Ulysses first had to go outward to Jupiter. It moved away from the star in order to change how it could return to the star's domain. The path shows how spaceflight often answers a question by accepting a long curve rather than a straight line. A direct climb above the Sun was too costly. A journey to a giant planet gave the spacecraft the angle it needed. Ulysses did not carry cameras designed to take detailed pictures of the solar poles. That was not its main purpose. It was a spacecraft for measuring the environment through which it moved. Its instruments sampled solar wind particles, magnetic fields, energetic particles, cosmic rays, dust, and radio and plasma waves. In this sense, it answered the question of what lies above and below the Sun by touch rather than by sight. It passed through the high-latitude solar environment and measured what was there. That distinction matters. A picture of the Sun from above would show the polar surface and the corona from a new angle, but Ulysses provided a different kind of knowledge. It moved through the space shaped by the Sun's poles. It recorded the flow of charged particles and the magnetic field carried with them, sampled the heliosphere not only where the planets travel, but in regions north and south of the familiar plane. The spacecraft became a probe of the space above and below, not merely an observer looking at it from afar. After Jupiter, Ulysses followed a long looping orbit around the Sun, passing over high southern latitudes and then high northern latitudes. Its first south polar pass came in 1994, followed by a north polar pass in 1995. Those years placed the spacecraft in regions no earlier mission had sampled so directly. It moved through solar wind that had not been measured from the usual near ecliptic position. It carried instruments into the part of the heliosphere that had previously been known mostly by inference and theory. At solar minimum, when the Sun's magnetic structure is more ordered and large polar coronal holes can dominate the high latitudes, Ulysses found a striking difference between the equatorial and polar solar wind. Over the poles, it encountered fast solar wind that flowed more steadily than the slower, more variable wind near the ecliptic. The spacecraft measured a high-latitude environment, that was not empty, not still, and not merely a thin extension of ordinary space. It was a broad stream of plasma and magnetic field moving outward from the sun. The word wind can be misleading because it invites the mind to think of air. Solar wind is not air. It is a thin flow of charged particles, mainly protons and electrons, released from the sun's outer atmosphere and carried through interplanetary space. It does not blow against skin or move leaves. It fills the solar system as a plasma, stretched by motion, structured by magnetic fields, and altered by the changing activity of the star that releases it. Ulysses measured that flow in regions humans had not directly crossed before. Above the sun, then, one of the first physical answers was fast solar wind. Below the sun, another answer was the same broad kind of flow, though changing with magnetic polarity and solar cycle conditions. The regions over the poles were not empty caps of space. They were channels through which solar material and magnetic structure extended outward. The spacecraft found that the sun's high latitudes had their own character, and that character depended on the cycle of solar activity. During its long mission, Ulysses observed the sun through more than one phase of the solar cycle. This was important because the high latitude heliosphere is not fixed. At solar minimum, the magnetic field tends to be more dipole-like, with large open polar regions and a clearer separation between fast polar wind and slower equatorial wind. At solar maximum, the pattern becomes more disturbed. The difference between polar and equatorial wind can weaken or become less orderly, and the heliosphere takes on a more complicated structure. The spacecraft's orbit allowed these changes to be measured from a position that Earth could not supply. Ulysses made nearly 3 full orbits around the Sun during more than 18 years of operation. Its long life turned a single exploration into a record. It did not merely glance above the solar system and return one isolated result. It revisited high latitudes as the sun changed, giving scientists a way to compare one solar condition with another from outside the ordinary viewing plane. A spacecraft moving through high solar latitude occupies a different kind of solitude from a telescope near Earth. It does not see the sun as a disk at the center of an image. It passes through a region where the sun's influence is already around it, carried in particles and field lines. The measurements arrive as numbers, variations, directions, speeds, and intensities. A magnetic field turns. A particle count rises. A plasma wave registers. The environment is read as a sequence of physical traces rather than as a visible landscape. Those traces helped clarify the three-dimensional heliosphere. Before Ulysses, much of the solar wind had been measured near the ecliptic because that is where Earth and most spacecraft travel. From that limited region, scientists could build models of how the wind might behave at high latitudes. Ulysses tested those models. It showed that the heliosphere above and below the planetary plane could differ in speed, composition, magnetic structure, and particle behavior. The sun's influence was not a flat, evenly spread surface. It was a volume with latitude. The spacecraft also measured cosmic rays, energetic particles that enter the heliosphere from outside the solar system or are accelerated within it. The solar wind and magnetic field affect how these particles move. By traveling to high latitudes, Ulysses helped show how cosmic ray intensity changes with position and solar activity. Above and below the sun, the question was therefore not only what the sun sends out, but also how the sun's expanding magnetic environment filters what comes in. Dust was part of the story as well. Ulysses detected tiny dust grains moving through interplanetary space, including particles linked to interstellar dust passing into the solar system. These grains were small, but their paths carried information about the environment through which they moved. The space above and below the sun was not crowded in any ordinary sense, yet it was not vacant. It contained plasma, fields, particles, and grains, all moving through a vast region shaped by solar gravity and magnetism. One of the mission's important lessons was that the sun cannot be fully understood from one latitude. The ecliptic gives an excellent view of many things, especially the region where Earth and the planets move. But the sun's magnetic field is global. Its wind fills space in all directions. Its poles help organize large-scale structure. A spacecraft that remains near the planetary plane samples only one band of that system. Ulysses showed that the missing latitudes were not decorative. They were necessary. The name Ulysses was fitting in a loose historical sense, though the mission's science remained far from mythology. It was a journey beyond the familiar route, a departure from the common plane. But its achievement did not come from adventure language. It came from measurements patiently gathered across years. The spacecraft passed over the sun's poles, crossed different solar latitudes, returned data through changing cycles, and gave heliophysics a view that had been missing from the flat architecture of earlier exploration. There is also a useful humility in what Ulysses did not do. It did not provide detailed polar images of the sun's surface. It did not solve every question about the solar dynamo or the polar magnetic field. It did not replace Earth-based observatories or later solar missions. Instead, it filled a different absence. It entered the high-latitude heliosphere and measured the conditions there directly. In science, that kind of partial answer can be more valuable than a broad claim. The mission helps separate two ideas that are often blended together in imagination: looking at the sun from above and moving through the space above the sun. Ulysses did the second. It passed over the solar poles in its orbit and sampled the flow of solar influence at high latitude. It gave scientists direct knowledge of plasma and fields above and below the usual planetary level. Later missions would seek the first more fully by tilting their view and imaging the solar poles themselves. As Ulysses moved through those high-latitude regions, the simple question became physically populated. Above the sun there was solar wind. Below the sun there was solar wind. There were magnetic fields, energetic particles, cosmic rays, dust grains, and changing structures tied to the solar cycle. The answer was not a single body waiting over the star. It was an environment, thin by earthly standards, but active across immense distances. The spacecraft's path also showed why above and below require effort to reach. The solar system's flatness is not a prison, but it is an inheritance. Earth gives every launch a starting motion near the ecliptic, and leaving that plane takes planning. Ulysses used Jupiter to do what a direct engine burn could not easily accomplish. Its high inclination orbit was therefore both a scientific instrument and a navigational achievement. The orbit itself was part of the discovery. By the time the Ulysses mission ended in 2009, after its power and communication limits had grown too severe, it had changed the way the sun's surroundings were understood. The heliosphere was no longer only a region measured near the planets. It had been crossed at high latitudes. The polar wind had been sampled. The sun's influence had been followed above and below the old plane. A more three-dimensional sun had begun to emerge from the data. That data pointed toward the next layer of the answer. Ulysses had measured the wind that flows from high latitudes, but the wind itself had origins closer to the sun, in the corona and in the magnetic structures that open outward from polar regions. To understand what Ulysses found above and below the sun, the flow has to be followed back toward the star, where fast streams of charged particles begin their outward passage. Chapter 6: The Fast Wind from the Poles. Fast solar wind is one of the clearest physical answers to the question of what lies above and below the sun. It is not an object resting over the star, and it is not a hidden planet or a separate layer of space. It is a flow. From high solar latitudes, especially during certain phases of the solar cycle, charged particles stream outward with a steadiness and speed that differ from the slower, more variable wind often measured closer to the ecliptic. The word wind has to be handled carefully here. On Earth, wind is air in motion, heavy enough to bend grass, move clouds, carry scent, and press against the face. Solar wind is not air. It is plasma, a thin flow of charged particles, mostly protons and electrons, released from the sun's outer atmosphere. It moves through interplanetary space while carrying part of the sun's magnetic field with it. No lungs could breathe it, and no ordinary sail would feel it as a breeze, yet it fills the space through which the planets move. Eugene Parker gave this flow its modern theoretical form in the 1950s. Before his work, the sun's outer atmosphere was often treated as something that might remain more nearly bound to the star. Parker argued that the corona was so hot that it could not stay static. It had to expand outward, becoming a continuous flow away from the sun. The idea was resisted at first, partly because it described the solar atmosphere not as a contained envelope, but as something constantly opening into space. Spacecraft later confirmed that Parker's solar wind was real. Measurements from early space missions showed streams of particles moving outward from the sun, carrying magnetic fields through the solar system. What had once been a theoretical necessity became an observed environment. Earth did not orbit through emptiness. It orbited inside the extended atmosphere of the sun, far beyond the visible surface and far beyond the bright disk that the eye recognizes. Ulysses added latitude to that understanding. Near the ecliptic, spacecraft had already measured solar wind for decades. They knew it varied in speed, density, and magnetic structure. But Ulysses moved through regions far above and below the usual planetary plane, where high-latitude conditions could be sampled directly. During solar minimum, when the sun's large-scale magnetic field was more ordered, the spacecraft found fast solar wind flowing from the polar regions with notable regularity. At high latitudes, this wind could reach speeds around 700 to 800 kilometers per second. Near the ecliptic, slower solar wind often moved closer to 300 to 500 kilometers per second, though conditions varied. These numbers are not fixed borders, but they help mark the difference Ulysses saw. The polar wind was not merely the ordinary solar wind placed somewhere else. It had a different character, tied to large coronal holes and open magnetic field structures near the sun's poles. A stream of charged particles moving hundreds of kilometers every second sounds violent in ordinary language, but the solar wind is extremely thin. Near Earth, only a few particles may occupy each cubic centimeter. Its force is not like a storm pressing against a wall. Its importance comes from persistence, reach, and magnetism. Over time and distance, the flow shapes planetary magnetospheres, carries disturbances from the sun, and fills the heliosphere with a moving plasma that never fully stops inside the sun's domain. The high latitude flow measured by Ulysses was connected to polar coronal holes. These are regions in the sun's corona where magnetic field lines are open to interplanetary space rather than closing back down into loops. In extreme ultraviolet and X ray observations, coronal holes often appear darker than their surroundings because the plasma there is less dense and somewhat cooler than neighboring coronal regions in those wavelengths. The darkness is not emptiness, it is a sign of structure. From such open regions, particles can escape outward more readily. The magnetic field does not trap them in closed arcs near the sun. It provides a route into space. During solar minimum, large polar coronal holes can cover broad, high-latitude areas, giving rise to fast streams that fill the heliosphere above and below the sun. This is why the polar regions matter far beyond their appearance in images. They are connected to the way the sun supplies space with plasma. The flow has texture in measurement rather than in sight. A detector does not see a river. It records particle speed, density, temperature, charge, and direction. A magnetometer senses the field carried outward through the plasma. Numbers change as the spacecraft crosses one region into another. A steady high-speed stream gives way to a slower or more disturbed one. The environment is thin, but not featureless. Its structure is written in variations. Ulysses showed that the solar wind was organized by latitude more strongly during solar minimum. Above and below the sun, fast wind dominated. Near the solar equator and closer to the ecliptic, slower and more variable wind was more common. This arrangement reflected the sun's simpler magnetic shape during that phase of the cycle when large polar coronal holes were well developed. The sun, in those years, resembled a more ordered magnetic body, with polar regions sending fast streams outward and equatorial regions carrying a more mixed flow. At solar maximum, the pattern became less clean. The sun's magnetic field grew more complex. Active regions appeared across broader latitudes. Coronal holes could occur in different places. The difference between polar and equatorial wind weakened, and the high latitude heliosphere became more variable. Ulysses was valuable because it survived long enough to witness more than one state of the sun. It measured not only where the fast polar wind existed, but how its dominance changed as the solar cycle advanced. This changing pattern also means that the question of what sits above and below the sun does not have one permanent answer. At one phase of the cycle, the high latitude regions may be filled by steady fast wind from polar coronal holes. At another phase, the same broad directions may contain more complicated streams, magnetic sectors, and disturbances. The geography of space above and below the Sun is partly a geography of time. The Sun changes, and the regions around it change with it. Magnetic polarity adds another layer. The solar wind carries the Sun's magnetic field outward, frozen into the plasma in the language of magnetohydrodynamics. Because the Sun rotates while the wind moves away, the field does not extend as straight lines like stiff wires. It forms a spiral structure, often called the Parker spiral, curving through interplanetary space. Above and below the Sun, the polarity of the field can differ depending on the solar cycle and the large-scale arrangement of the magnetic field. The heliospheric current sheet marks a boundary where magnetic polarity changes across a broad wavy surface extending outward from the Sun. Near solar minimum, this sheet can be less warped, allowing clearer separation between northern and southern magnetic regions. Near solar maximum, it becomes more distorted. Although the term sheet sounds flat, the structure is not a solid surface. It is a vast magnetic boundary carried through moving plasma, shaped by the rotating Sun. The fast polar wind therefore belongs to a larger system. It is not only material leaving the corona, it is part of the Sun's magnetic architecture, part of the heliosphere's shape, and part of the cycle through which the star reorganizes itself. Above and below the Sun, the wind carries information about the polar fields, the state of the corona, and the phase of solar activity. A particle measured far from the solar surface can still carry the signature of the region from which it came. For Earth, the polar wind is not as directly central as the slower and more variable wind that commonly reaches the near ecliptic environment. Earth orbits close to the plane where equatorial solar conditions often matter most. But understanding the polar wind helps scientists understand the global Sun. A star cannot be understood only through the band that happens to contain one planet. Its high latitudes help shape the background through which all solar disturbances travel. Above the Sun, then, there may be a fast stream of plasma moving outward from open magnetic regions. Below the Sun, another stream may move through the opposite high latitude hemisphere. These flows can be steady or disturbed, separated or mixed, depending on the solar cycle. They are thin beyond ordinary intuition, and yet large enough to fill volumes of space that dwarf the orbits of planets. The answer is both sparse and immense. This is where the earlier geometry becomes physical. The ecliptic gave a plane. The Sun's rotation gave an axis. Ulysses gave measurements from high latitude. The fast solar wind gave those directions content. Above and below the Sun are not just positions on a map, they are routes along which the solar atmosphere continues outward, carrying particles and magnetic field away from the star. To understand why the fast wind leaves most clearly from certain regions, the path has to be followed back into the corona. There, the Sun's magnetic field does not always close back on itself in glowing loops. In some places, especially near the poles during quieter phases of the cycle, it opens outward into space. Those dark-looking regions in high-energy images are not empty wounds in the Sun, but coronal holes, and they are one of the main reasons the space above and below the sun is filled by such fast moving flow. Chapter 7: Coronal Holes and Open Fields. Coronal holes are among the clearest places where the sun seems to open into space. They are not holes in the ordinary sense. Nothing has been punctured, and no solid surface has been broken. The sun has no crust to tear and no roof to split. A coronal hole is a region in the corona where the plasma is less dense and cooler than surrounding coronal material in certain wavelengths, so it appears darker in extreme ultraviolet and X-ray images. The darkness matters because it reveals structure. In visible light, the sun can appear as a bright disk with spots, granulation, and occasional features seen through special filters. In extreme ultraviolet images, the corona becomes a changing network of loops, arcs, darker patches, and extended regions tied to magnetic fields. Coronal holes stand out because they do not glow with the same density of trapped hot plasma. Their appearance is quiet, but their meaning is active. They mark places where the sun's magnetic field is arranged differently. Most coronal structures are shaped by magnetic fields that loop back toward the sun. Plasma follows those fields, and the result can be bright arches suspended above active regions. These loops are not rigid objects. They are magnetic pathways filled with hot charged material rising from one part of the solar surface and returning to another. In such regions, the field is closed. Material may move along it, heat within it, and radiate from it, but it does not have the same open route into interplanetary space. Inside coronal holes, the magnetic field is more open. Field lines extend outward rather than closing nearby. The language of field lines is a way of visualizing direction and connection. No physical string runs out of the sun. Still, the concept is useful because charged particles respond strongly to magnetic structure. Where the field opens outward, plasma can flow away more easily, becoming part of the solar wind. In this way, a dark region in a solar image can correspond to a broad route through which solar material leaves the star. Eugene Parker's solar wind theory gave this picture its deeper physical setting. In the late 1950s, Parker argued that the sun's hot corona could not remain static. If the corona had such high temperature, its gas pressure would drive material outward into space. The idea was not immediately welcomed. Some reviewers and scientists doubted that the sun could be continuously losing material in this way. But spacecraft measurements soon showed that a stream of charged particles was indeed moving through interplanetary space. Parker's insight made the sun larger in a physical sense. The bright sphere was no longer the whole solar environment. The corona did not simply fade into stillness above the visible surface. It became the inner part of an outward flow. The solar wind carried the sun's influence far beyond the orbit of Earth, past the outer planets, and into the heliosphere. The space above and below the sun was therefore not separate from the sun. It was filled by material that had once belonged to the sun's atmosphere. Coronal holes explain why that outward flow is not uniform everywhere. The solar wind can be fast or slow, more steady or more variable, shaped by the magnetic environment from which it emerges. Polar coronal holes, especially during solar minimum, are associated with fast solar wind. They can occupy large regions around the sun's poles, sending streams of plasma into high latitude space. Ulysses measured the result far from the solar surface, but the source lay closer in, where open magnetic fields gave the wind a path. During solar minimum, the sun's large-scale magnetic field often takes on a simpler form than it has during more active periods. Large coronal holes can form around the poles, and the heliospheric current sheet becomes less strongly warped. Fast wind from the polar regions spreads into broad, high-latitude domains. Near the ecliptic, slower wind and more variable streams are common. This makes the space above and below the sun physically distinct from the space closer to the planetary plane, at least during those more ordered parts of the cycle. Solar maximum changes the arrangement. Active regions become more numerous. Magnetic fields grow more tangled in their large-scale pattern. Coronal holes can appear at lower latitudes or take on more irregular shapes. The clean separation between polar fast wind and equatorial slow wind becomes less stable. Above and below the sun still contain solar wind and magnetic field, but their structure is no longer as neatly divided. The sun's activity rearranges the routes by which plasma leaves. A coronal hole can last for several solar rotations, especially during quieter phases. As the sun turns, a coronal hole facing Earth can send a stream of faster solar wind outward in Earth's direction. When that stream reaches near Earth space, it can interact with Earth's magnetic field and contribute to geomagnetic activity. In this way, a dark-looking region on the sun can become part of a chain that reaches a planet days later. The connection is not theatrical. It is a measured path through plasma and field. The polar coronal holes are more remote from Earth's usual line of sight, but they matter for the global shape of the heliosphere. When open magnetic fields dominate the high latitudes, they help organize how solar wind fills space above and below the ecliptic. They also carry information about the sun's magnetic polarity. The north and south polar regions can have opposite magnetic signs, and those signs reverse over the solar cycle. A map of coronal holes is therefore also a map of changing magnetic order. Extreme ultraviolet telescopes made coronal holes easier to study because they show the corona in light emitted by highly ionized atoms. Different wavelengths reveal plasma at different temperatures. In these images, a coronal hole may look like a dim patch against brighter surroundings. The image can seem simple, but the interpretation depends on magnetic measurements, solar rotation, wavelength, and context within the solar cycle. A dark patch is not enough by itself. It becomes meaningful when joined to the field structure beneath it and the wind measured beyond it. There is a useful restraint in how these regions should be imagined. A coronal hole is not a tunnel. It does not have walls, and it does not lead into a separate chamber of space. It is a region where the corona has a different density and magnetic arrangement. The plasma is thinner there, the field opens outward, and the solar wind can escape more readily. The word hole survives because the images look dark, but the physics is not emptiness. It is openness. That openness gives the episode's main question another layer. Directly above the sun, if the frame is solar north, one may find a polar coronal hole during certain phases of the cycle, with open magnetic fields extending outward. Directly below the Sun, in the southern high latitudes, a corresponding region may form with its own magnetic polarity and structure. These regions do not sit motionless like caps placed over the star. They grow, shrink, shift, and reorganize as the Sun's magnetic field evolves. The open fields also explain why solar direction is not only geometric. A coordinate system can define solar north and south, but magnetic fields give those directions physical behavior. Above and below the Sun are not just empty extensions of an axis. They are paths along which plasma may leave more freely. They are regions where the Sun's atmosphere becomes part of interplanetary space. The axis gives direction, the field gives structure. Ulysses measured the high latitude wind far from the Sun. Solar observatories saw dark coronal holes closer to the surface. Parker's theory connected the hot corona to the outward flow. Together, these pieces formed a more complete answer than any one of them could provide alone. A spacecraft in high latitude could detect fast plasma. A telescope could see the coronal source region. Theory could explain why the corona must expand. The space above and below the Sun became a connected system. Still, the view from near the ecliptic left the polar source regions partly compressed and uncertain. Coronal holes near the poles could be inferred, mapped, and watched, but their true shapes remained difficult to measure from the side. The same problem returned. Instruments had improved, theory had advanced, and spacecraft had sampled high latitude wind, yet the Sun's polar face itself still needed a better angle. The next step required a mission built not only to measure the environment around the spacecraft, but to tilt the view of the Sun itself. Chapter 8: Solar Orbiter Tilts the View. Solar Orbiter was built around a different kind of solar ambition. It did not only need to go closer to the Sun, it needed to see the Sun from angles that Earth could not provide. For centuries, and then through most of the space age, the Sun had been watched from near the same broad plane in which Earth travels. Instruments improved, wavelengths multiplied, images sharpened, and measurements deepened, but the viewpoint remained close to the ecliptic. Solar Orbiter was designed to change that slowly. The mission is a collaboration between the European Space Agency and NASA, launched in February 2020. Its path around the Sun is not a simple inward fall. It uses repeated flybys of Venus to reshape its orbit, gradually lifting the spacecraft out of the ecliptic plane. This is patient orbital engineering. Venus does not simply pull the spacecraft closer to the Sun, it helps alter the tilt of the orbit, giving Solar Orbiter access to solar latitudes that earlier imaging missions could not reach in the same way. That slow increase in inclination is central to the mission's purpose. A spacecraft near Earth can look at the Sun with powerful instruments, but it sees the poles from the side. Solar Orbiter moves toward a geometry in which the poles become less compressed near the edge of the disk. It does not immediately fly over the Sun's pole in a dramatic leap. It builds the angle over time, orbit by orbit, encounter by encounter, until a region long seen obliquely begins to open. Solar Orbiter also differs from Ulysses in the kind of knowledge it gathers. Ulysses traveled through high-latitude regions and measured particles and fields around the spacecraft, but it did not image the solar surface in detail. Solar Orbiter carries both in situ instruments and remote sensing instruments. It can measure the solar wind, magnetic field, energetic particles, and plasma waves where it is, while also looking back toward the sun's atmosphere and surface. It joins touch and sight. That combination matters because the sun is not only an object to be photographed, it is a source of flowing material and magnetic structure. A remote image can show a coronal hole, an active region, or a polar magnetic pattern. A local instrument can measure the wind and fields that arrive at the spacecraft. When both kinds of measurement are joined, scientists can begin to connect what leaves the sun with the region from which it came. Solar Orbiter was made for that connection. The spacecraft's instruments form a careful division of labor. Some watch the sun directly in visible, ultraviolet, and extreme ultraviolet light. Some measure magnetic fields at the spacecraft. Others detect charged particles, radio waves, plasma conditions, and energetic particles. The result is not a single camera pointed at a bright disk, but a mobile solar observatory moving through the environment it studies. Each orbit gives another arrangement of distance, angle, and solar activity. In March 2025, Solar Orbiter reached a point that gave it a new kind of view of the Sun's south pole. The angle was still modest in absolute terms, roughly in the range of the mid-teens below the solar equator, but it was enough to produce views that had not been available before. The south polar region could be seen from outside the usual flat perspective. A small change in angle became a large change in meaning because the old view had been so constrained. The first high angle polar views were not important because they made the sun look unfamiliar in a decorative sense. They mattered because the polar magnetic field is difficult to measure from near the ecliptic. Near the limb of the solar disk, projection effects complicate the data. A better angle improves the ability to connect surface magnetism, coronal structure, and solar wind sources. The pole becomes less like a compressed border and more like a region that can be examined. Solar Orbiter's polarimetric and helioseismic imager helps measure the magnetic field and motion at the solar surface. Its extreme ultraviolet imager shows the corona and transition region structures. Other instruments trace plasma, fields, and particles around the spacecraft itself. Together, they allow a question to be followed across distance. What magnetic pattern exists near the pole? What coronal structure rises above it? And what kind of solar wind moves outward from that region? The tilted view also changes how coronal holes can be understood. From near the ecliptic, a polar coronal hole can appear pressed against the edge of the solar image. Its boundary may be difficult to trace. Its relation to the exact pole may depend on corrections and models. From a higher latitude, the same region can be seen with less distortion. The dark patch in extreme ultraviolet becomes less like a narrow mark at the rim and more like a structure spread across a polar cap. This is not only a matter of better pictures. The sun's poles are tied to the solar cycle. Polar magnetic fields help shape the next cycle of activity. They reverse polarity as the cycle progresses, and their strength can provide clues about what may follow. If those fields are poorly measured, then the global magnetic map of the sun remains incomplete. Solar Orbiter's changing perspective helps fill that missing part of the map. The mission's timing also matters. Solar activity rises and falls across an approximately 11-year cycle, and solar orbiters' early polar viewing occurred during an active period of the current cycle. This means the poles were not being viewed as permanently quiet caps. They were being seen during a time when the sun's magnetic system was reorganizing. Observations from such periods can help scientists understand not only what the poles look like, but how they change while the entire star moves through its cycle. A tilted view has a physical softness to it. The round disk no longer presents itself only as a face. A hidden curve begins to show more of its upper or lower surface. Features that once clung to the edge move inward. Lines of latitude gain space. The pole remains part of the same star, but the geometry stops flattening it so severely. A change of angle allows the sun to recover some of its depth. From solar orbiter's path, above and below the sun become observational directions rather than only inferred ones. The spacecraft does not merely say that solar south exists because coordinates require it. It begins to see south as a region with magnetic texture, coronal pattern, and connection to the surrounding heliosphere. The answer to the episode's question becomes less theoretical. There is not one object below the sun. There is a polar environment, and a spacecraft has begun to look into it. The use of Venus flybys gives the mission a slow, accumulating rhythm. Each encounter adjusts the orbit. Each adjustment gives a slightly different solar viewpoint. Future passes are expected to raise solar orbiter's inclination farther, improving its view of both polar regions. This gradual lifting is part of the mission's character. It does not conquer the polar view in one movement. It approaches it through repeated geometry. Solar Orbiter also helps clarify the difference between proximity and perspective. A spacecraft may fly very close to the sun and still remain near the ecliptic. Another may stay farther away at times, but see from a more useful angle for polar science. The sun is not one problem. It is many problems layered together. Heat, magnetic fields, plasma flow, particle acceleration, rotation, and latitude all require different kinds of access. The mission, therefore, stands between two earlier limitations. Earth-based and near-Earth observatories saw the sun constantly, but mostly from the side. Ulysses traveled above and below the sun, but did not image the polar surface in detail. Solar Orbiter combines a tilted viewpoint with instruments that can watch the sun and measure the surrounding plasma. It is not a replacement for those earlier efforts. It is the next piece in a longer correction of perspective. As its orbit rises farther from the ecliptic, the question of what sits directly above and below the sun becomes more observationally grounded. The answer includes polar magnetic fields, coronal holes, open structures, and solar wind sources. But those words now belong to regions that instruments can examine from a better angle. The old flat view of the sun begins to bend into a fuller sphere, and the poles become part of the visible story of the star. Chapter 9: The Magnetic Cycle Turning Over. The sun's poles matter most when the sun is changing. Seen in ordinary light, the polar regions may appear less dramatic than the belts where sunspots gather, split, darken, and fade. The eye is naturally pulled toward the active zones, where bright regions and dark markings make the star look busy. But the large-scale magnetic life of the Sun cannot be understood only through the parts that look most active. Near the poles, the Sun carries fields that help mark where one cycle is ending and another is being prepared. The solar cycle is usually described as lasting about 11 years, measured from one sunspot minimum to the next. That number is useful, but it is only part of the deeper magnetic rhythm. Sunspot counts rise and fall over roughly 11 years, yet the Sun's magnetic polarity takes about 22 years to return to the same full arrangement. During one 11-year rise and fall, the magnetic poles reverse. North becomes south in magnetic sign, and south becomes north. During the next cycle, they reverse again. The visible sunspot cycle is therefore one half of a longer magnetic turn. This means the Sun's north and south are not fixed in the way Earth's geographic poles are fixed. The rotation axis remains the reference for solar north and solar south, but the magnetic identity of those regions changes. A polar field that once pointed outward may later point inward. The opposite pole changes with it. The star does not keep one permanent magnetic arrangement. It reorganizes itself through plasma motion, field stretching, emergence, cancellation, and transport across the solar surface. The difficulty begins with the fact that the Sun is not solid. Earth's magnetic field is generated deep inside the planet by motion in its liquid outer core, while the surface above is comparatively stable. The Sun's magnetic field is generated in a rotating, convecting plasma body, where the outer layers themselves move, shear, and circulate. The equator rotates faster than higher latitudes. Hot material rises and cooler material sinks in convective patterns. Magnetic fields are carried by that motion, stretched by it, folded by it, and brought again to the visible surface. Sunspots are the most familiar visible signs of this activity. They often appear in pairs or groups with opposite magnetic polarities, like places where a magnetic loop has emerged through the photosphere. At the beginning of a cycle, sunspots tend to appear at higher solar latitudes, away from the equator. As the cycle progresses, new spots appear closer and closer to the equator. When their positions are plotted across time, the pattern forms the butterfly diagram, with two broad wings narrowing inward in the northern and southern hemispheres. That diagram gives latitude a memory. It shows that solar activity is not scattered randomly across the surface. It migrates. It follows a pattern that repeats imperfectly from cycle to cycle. Above and below the solar equator, the two hemispheres carry their own activity bands. Sometimes the north is stronger, sometimes the south leads. Their timing can differ, their sunspot numbers can differ. The Sun is one star, but its two hemispheres do not always move through the cycle in perfect step. Horace Babcock offered one of the important 20th century models for understanding how the Sun's magnetic cycle works. In 1961, he described a picture in which the Sun's differential rotation stretches magnetic field lines. Sunspot regions emerge from the twisted field, and the remnants of those regions are transported across the surface in ways that help reverse and rebuild the polar fields. Later work has refined the model, but its basic insight remains important. The polar fields are not isolated. They are linked to the decay and redistribution of magnetic regions from lower latitudes. A sunspot group does not simply disappear when it fades from view. Its magnetic flux can disperse across the solar surface. Some of that magnetic material cancels with opposite polarity nearby. Some is carried by flows toward the poles. Over time, the accumulation of transported magnetic flux can weaken the existing polar field, cancel it, and then build a new field of the opposite polarity. The quiet polar region is therefore connected to the visible activity belts by a slow surface process. The flow that carries magnetic flux poleward is called meridional circulation. It is not fast in ordinary terms. It moves at speeds of only meters per second, far slower than the dramatic motions people associate with solar activity. But the sun is large and the cycle is long. A slow flow sustained across years can matter greatly. It can help move magnetic remnants from decaying active regions toward high latitudes, where they contribute to the polar field reversal. This gives the poles a predictive role. The strength of the polar field near solar minimum is one of the indicators scientists use when estimating the possible strength of the next solar cycle. A stronger polar field can suggest a stronger following cycle, though the details are complex and not perfectly settled. A weaker polar field can suggest a weaker one. The poles, which seem visually subdued compared with sunspot belts, carry information about what the sun may do later. The physics has a slow turning quality. Magnetic regions emerge in the active belts, break apart, spread, and leave traces that drift across the surface. The remnants move poleward over months and years. Near the poles, they meet the older field, reduce it, replace it, and establish a reversed arrangement. Nothing about this process looks like a simple switch being flipped. It is a gradual reworking of the star's outer magnetic pattern, carried out by flows that are difficult to see directly, but visible through their accumulated consequences. From Earth's usual viewpoint, the polar part of this process is especially hard to measure. The magnetic field near the poles is often weak compared with active regions, and the line of sight angle is poor. Instruments can infer, reconstruct, and correct, but the geometry remains limiting. The very regions that may help forecast the next cycle are the regions seen from the least favorable angle. Solar orbiters' tilted views matter because they begin to reduce that old uncertainty. The polar field reversal usually happens around the time of solar maximum, though not always at the same moment in both hemispheres. One pole may reverse before the other. The process can be uneven, with temporary mixed polarity regions and lingering patches of old field. The sun's magnetic cycle is regular enough to be recognized, but not so regular that it behaves like a clock. Each cycle carries its own asymmetries, delays, and strengths. That irregularity is one reason the poles are scientifically valuable. If the solar cycle were perfectly mechanical, a simple count of years would be enough. But the sun's activity varies. Some cycles are strong, with many sunspots and intense magnetic complexity. Others are weaker. The timing of rise and decline can differ. Polar field measurements give scientists another way to read the cycle from within the sun's own magnetic structure, rather than only from the number of visible spots. The solar dynamo is the larger name for the process that generates and sustains the sun's magnetic field. The word dynamo points to conversion. Motion inside an electrically conducting fluid or plasma creates magnetic field. In the sun, rotation, convection, shear, and circulation all contribute. The details remain an area of continuing research, especially because the sun cannot be opened, sampled, or simplified like a laboratory machine. Scientists infer its interior motion through helioseismology, surface observation, magnetic mapping, and models. Near the tachocline, a transition region between the radiative interior and the convective outer zone, strong shear is thought to play a major role in organizing magnetic fields. Higher up, the convection zone churns and transports energy outward. At the surface, magnetic fields emerge, disperse, and migrate. The polar fields are therefore the visible upper part of a system rooted deeper inside the star. They are not the whole dynamo, but they are one of the ways the hidden dynamo writes itself onto the observable sun. There is a useful quietness in the polar evidence. Sunspots announce themselves as dark regions against bright plasma. Flares release sudden energy. Coronal mass ejections send large structures outward into space. Polar fields, by contrast, often speak through weaker measurements and long-term patterns. Their importance is not obvious in a single dramatic image. It appears when solar data are placed across years, when one cycle fades into another, and when the next rise of activity begins to take shape. The connection between polar magnetic fields and solar wind also returns the discussion to the space above and below the sun. During periods when polar coronal holes are strong, open magnetic fields near the poles help guide fast wind into high-latitude space. As the cycle advances and the polar fields reverse, the structure of those open regions changes. The wind measured above and below the sun is therefore connected to the same cycle that reshapes the surface field. Space around the sun carries the history of magnetic change. This is why a spacecraft measuring high-latitude solar wind is not only sampling particles, it is sampling part of the magnetic cycle extended into space. The wind carries magnetic polarity outward. The heliosphere responds to the sun's changing field. The current sheet warps more or less strongly depending on the phase of the cycle. Cosmic rays entering the heliosphere are filtered differently as solar activity rises and falls. The poles influence not just the solar surface, but the conditions through which planets and spacecraft move. The phrase above and below now contains time as well as direction. Above the sun during one part of the cycle may mean fast wind from a stable polar coronal hole. Above it during another may mean a more complex and changing high-latitude environment. Below the sun may carry the opposite magnetic polarity, then later a reversed one. The regions are not static shelves above and beneath the star. They are moving chapters in the sun's magnetic cycle. For observers, this makes direct polar measurements especially important. A view from near the ecliptic can follow sunspots across the disk and study many active regions well, but it struggles with the exact fields near the poles. A mission that rises out of that plane can help show whether the polar field is strengthening, weakening, reversing, or breaking into mixed structures. Better polar data can feed better models of the dynamo and better forecasts of future solar activity. The problem is not only academic. Solar activity affects space weather. Disturbances from the sun can influence satellites, radio communication, navigation systems, power grids, and astronauts beyond Earth's protective atmosphere. The polar fields do not produce every disturbance directly, but they help shape the solar cycle that governs the background level of activity. A fuller understanding of the poles is part of a fuller understanding of the sun's changing influence on the space around Earth. At this point, the sun's poles have become more than the endpoints of an axis. They are magnetic reservoirs, transition regions, and signs of the next cycle forming. They are tied to the slow transport of decayed active regions, the reversal of polarity, the opening of coronal holes, and the fast wind that fills high latitude space. They are places where the sun's visible surface and invisible field meet the wider heliosphere. The question that began with direction has therefore moved into rhythm. Above and below the sun are not only spatial answers, they are parts of a system that turns over, reverses, and rebuilds itself across years. The high latitude regions carry the traces of yesterday's active belts and the seeds of tomorrow's solar cycle. Beyond them, the solar wind continues outward, carrying the changing magnetic pattern into a much larger volume of space. Chapter 10: The Heliosphere Above and Below. Far beyond the visible edge of the sun, the solar wind continues outward. It thins as it travels, but it does not end near the planets. It carries charged particles, magnetic fields, and the slow imprint of the sun's rotation into a volume of space much larger than the familiar planetary system. This volume is called the heliosphere. It is the great region shaped by the sun's outward flow, and it gives the question of what lies above and below the sun its largest scale. The heliosphere is not a clear shell that can be seen with ordinary eyes. It is not a glass sphere around the planets, and it does not have a surface like the skin of a bubble. It is a physical domain defined by the solar wind pressing outward against the surrounding interstellar medium. Inside it, the sun's particles and magnetic field dominate the local environment. Outside it, the material between the stars becomes more important. The boundary is not a wall, but a transition. Above and below the sun, the heliosphere extends in three dimensions. It does not spread only along the ecliptic, and it does not belong only to the level where the planets move. The solar wind leaves the sun in all directions, though not with identical speed or structure everywhere. At high latitudes, especially during solar minimum, fast wind from polar coronal holes can fill broad regions above and below the planetary plane. Near the ecliptic, slower and more variable wind often carries a different texture of solar activity. This means the heliosphere is not a flat disk, it is a shaped volume. The planets travel through one broad belt of it, but the sun's influence rises above that belt and extends below it. The space above the sun contains solar wind, magnetic fields, energetic particles, cosmic rays entering from outside, and the long reach of the solar cycle. The space below contains the same kinds of things, arranged according to the sun's magnetic polarity, the phase of the cycle, and the structure of the outward flow. The solar wind does not move through space like water from a fountain in straight, simple lines. The sun rotates while the wind travels outward. Because of that rotation, the magnetic field carried by the plasma curves into a spiral pattern, often called the Parker spiral. Near the sun, the field points more directly outward. Farther away, the rotating source causes it to wrap through interplanetary space in a broad curve. Every planet moves through that curved magnetic environment. Above and below the sun, the spiral is still present, but the geometry changes with latitude. The high latitude wind measured by Ulysses showed that the heliosphere had a different character away from the ecliptic. During quieter solar periods, The polar regions sent out fast streams that were more steady than many near equatorial flows. The sun's magnetic field, carried outward by that wind, helped define northern and southern regions of the heliosphere. These regions were not separated like rooms. They were connected parts of a moving plasma system. The heliospheric current sheet is one of the largest structures in this system. It is the broad surface where the magnetic polarity carried by the solar wind changes sign. Because the sun's magnetic axis is tilted relative to its rotation, and because the sun itself rotates, this sheet becomes warped, often compared to a wavy skirt extending outward through the solar system. The comparison is imperfect, but it helps convey the shape. The current sheet is not solid. It is a magnetic boundary moving outward with the solar wind. Near solar minimum, the current sheet can be less warped. The heliosphere then has a more ordered north-south magnetic arrangement, with fast polar wind occupying high latitudes, and the current sheet lying closer to the ecliptic. Near solar maximum, the sheet becomes more distorted as the sun's magnetic field grows more complex. The high latitude regions become less simple, and the difference between above, below, and near the planetary plane becomes harder to divide cleanly. A spacecraft crossing this environment does not encounter the heliosphere as a visible landscape. It meets it through instruments. A magnetometer records field direction and strength. Particle detectors measure the speed, density, and temperature of plasma. Cosmic ray detectors count energetic particles arriving from distant sources. Dust detectors register tiny grains passing through the spacecraft's path. The heliosphere is known through these readings, accumulated across decades and stitched into a three-dimensional picture. Ulysses provided one kind of stitch. By moving to high solar latitudes, it measured the heliosphere above and below the sun's usual planetary level. Voyager provided another. The two Voyager spacecraft moved outward through the outer solar system and eventually crossed into interstellar space, passing through distant boundary regions where the solar wind slows and the sun's influence gives way to the surrounding medium. They did not explore high solar latitudes in the same way Ulysses did, but they showed how far the sun's domain extends. Together, such missions make the sun feel less like a bright object at the center of a diagram and more like the source of an environment. Earth is not merely orbiting a star at a distance of 1 astronomical unit. It is immersed in the star's extended influence. So are the other planets. So are the spaces between them, above and below the sun, beyond the poles and beyond the ecliptic. That influence continues as the heliosphere, carrying the trace of the star into the space between stars. The boundary of the heliosphere is usually described through several regions. The termination shock is where the solar wind slows from supersonic speeds as it begins to feel the pressure of the interstellar medium. Beyond that lies the heliosheath, a broader region of slower, disturbed solar wind. Farther out is the heliopause, where the solar wind's outward pressure and the interstellar medium's inward presence reach a balance. These boundaries are distant, variable, and shaped by direction. The heliosphere may not be perfectly round. Its shape depends on the solar wind, the sun's motion through the local interstellar medium, and the magnetic fields outside the solar system. Earlier images often showed it with a long comet-like tail, stretched behind the sun's motion. More recent models have suggested more complex shapes, including structures that may be less like a simple comet tail and more compact or multi-lobed. The exact global form remains an active subject of research because the heliosphere is too large to see all at once. This uncertainty does not erase the basic answer. Above and below the Sun, at the largest scale, lies the heliosphere, not empty darkness, not a vacant upper and lower space, but the continuation of the Sun's plasma environment. The star's wind expands outward, its magnetic field curves and folds through space, and its activity cycle alters conditions across distances that no ordinary sense of weather can contain. The Sun makes a region around itself, and the planets move inside it. Cosmic rays make the heliosphere's structure especially important. These high-energy particles arrive from beyond the solar system, many from distant astrophysical sources. The Sun's magnetic field and solar wind affect how easily they enter the inner solar system. During periods of high solar activity, the heliosphere can become more effective at modulating cosmic rays, reducing the number that reach Earth. During quieter periods, more can enter. The space above and below the Sun is part of that filtering system. At high latitudes, cosmic ray behavior helped Ulysses reveal the heliosphere's three-dimensional nature. If the solar environment were the same in every direction, latitude would matter little. But Ulysses measured differences linked to position, magnetic structure, and solar activity. A particle entering the heliosphere does not move through a neutral emptiness. It passes through a changing magnetic volume, and that volume is shaped in part by what the Sun sends out from its poles and equatorial regions. The heliosphere also carries disturbances outward. A coronal mass ejection, a fast stream, or a magnetic structure leaving the Sun can travel through interplanetary space and alter conditions far from the solar surface. Near the ecliptic, such disturbances matter for Earth and spacecraft around it. At higher latitudes, related structures move through regions less often sampled directly. Above and below the Sun, the heliosphere may carry the same solar cycle in forms that are harder to observe, but no less physical. This is where the idea of a solar atmosphere becomes much larger than the bright corona seen during an eclipse. The corona is the hot outer atmosphere near the Sun. The solar wind is the continuation of that atmosphere into space. The heliosphere is the volume made by that continuation as it presses outward into the interstellar medium. A person looking at the Sun sees a disk of light. Instruments reveal a star whose outer presence reaches beyond all the planets. The planets occupy only a small portion of this volume. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all move within the heliosphere, but none of them defines its full shape. Even the outer planets are far inside the Sun's extended domain compared with the distant boundary crossed by the Voyagers. Above and below the planetary plane, that same domain continues, less visited by spacecraft, less familiar in diagrams, but still structured by the Sun. The Sun's poles matter within this largest structure because they help organize the high-latitude flow that feeds the heliosphere. During certain phases of the solar cycle, polar coronal holes send fast wind outward into broad northern and southern regions. The magnetic polarity of those regions changes as the cycle turns. The heliospheric current sheet adjusts, warps, and shifts. What begins as magnetism on the Sun becomes architecture in space. A useful way to hold the idea is to separate emptiness from thinness. The space above and below the Sun is extremely thin by earthly standards. A cubic centimeter may contain only a few particles in some regions, and the distances are vast enough that ordinary intuition has almost nothing to hold. But thin is not the same as empty. Plasma can be thin and still carry magnetic fields. A field can be invisible and still guide charged particles. A boundary can be diffuse and still mark a real physical transition. The heliosphere is therefore one of the largest answers to the title question. Directly above and below the Sun, close in, there are poles, coronal holes, magnetic fields, and fast streams of solar wind. Farther out, those streams become part of a broad magnetic volume that surrounds the planetary system. Farther still, that volume meets the surrounding interstellar medium. The direction begins near the Sun, but it does not stop there. This larger view also helps explain why no single spacecraft can answer the question alone. Ulysses sampled high latitudes. Solar Orbiter began to image the poles from a better angle. Parker Solar Probe approaches the Sun closely. Voyager crossed distant boundaries. Each mission touches a different part of the same structure. The suns above and below are not located at one distance, and they are not revealed by one instrument. They stretch from the polar corona to the outer heliosphere. By this point, the old picture of the solar system as a flat arrangement of planets around a star has become insufficient. The ecliptic remains useful, but it is only one slice through a larger environment. Above that slice, the sun's wind continues. Below it, the same outward influence spreads. Around all of it, the heliosphere forms a changing boundary between the star and interstellar space. The next contrast is important because nearness alone can seem like the obvious solution. If a spacecraft goes closer to the Sun than any mission before it, it might seem that it must also answer the deepest questions about what lies above and below. But a close approach near the familiar plane is not the same as a polar view, and one of the most daring solar missions shows that distance and angle reveal different truths. Chapter 11: What Parker Cannot See from the Edge. Parker Solar Probe is one of the most intimate missions ever sent toward the Sun. Its path carries it closer to the solar surface than any spacecraft before it, into regions where the Sun is no longer only a bright object in the distance, but the immediate source of the surrounding environment. It moves through heat, radiation, magnetic fields, and plasma conditions that earlier missions could only study from farther away. In public imagination, that closeness can make Parker seem like the spacecraft that should answer every question about the Sun. But nearness is not the same as perspective. A spacecraft can come extremely close to the Sun while still remaining near the broad plane in which Earth and the other planets move. It can pass through the corona, measure the solar wind near its birthplace, and return data from a region no spacecraft had crossed before. While still not looking down over the poles, the Sun does not reveal itself through distance alone. It reveals different things to different paths. Parker's Solar Probe was launched in August 2018, named for Eugene Parker, whose theory of the solar wind changed the understanding of the Sun's outer atmosphere. The mission uses repeated flybys of Venus to reduce its orbital energy, allowing it to fall into closer and closer passes around the Sun. Each encounter adjusts the spacecraft's path, drawing its perihelion inward. Its closest approaches bring it within only a few million miles of the solar surface, an extraordinary distance in engineering terms, but still a particular kind of access. That access is inward rather than polar. Parker dives toward the Sun through an orbit that remains comparatively close to the ecliptic. It studies the near Sun environment, the place where the solar wind is being accelerated, where magnetic structures are still close to their source, and where the corona transitions into the outward flowing plasma that fills the heliosphere. This is a different question from what lies directly above and below the Sun's poles. Parker can measure beginnings, but not from every latitude. The mission's heat shield makes this possible. The thermal protection system, a carbon composite shield, faces the Sun during closest approaches and keeps the spacecraft's instruments within survivable temperatures. Behind that shield, Parker operates in a narrow, protected shadow. The Sun-facing side receives intense radiation, while the spacecraft body and many instruments remain guarded. The arrangement is not dramatic in the way an image of flame might suggest. It is a controlled geometry of exposure and protection. This shielded nearness gives Parker access to the corona, the Sun's outer atmosphere. The corona is visible from Earth during total solar eclipses as a pale, extended glow surrounding the darkened disk of the Moon. In instruments, it becomes a structured environment of plasma and magnetic fields, full of streamers, loops, open regions, and flows. Parker moves through parts of this environment directly. Instead of only watching the corona from far away, it samples particles and fields within it. Its instruments measure electric and magnetic fields, plasma particles, energetic particles, and visible light structures in the solar corona and solar wind. The Field's instrument suite studies fields and waves. SWEEP measures electrons, protons, and alpha particles in the solar wind. ISI studies energetic particles. WHISPER, the wide field imager for Parker Solar Probe, images coronal and heliospheric structures from within the region Parker is crossing. These instruments turn proximity into physical data. One of Parker's central goals is to understand how the solar wind is accelerated. Far from the Sun, the wind has already become an established flow. Near the Sun, the process is still being shaped. Magnetic fields bend, reconnect, fluctuate, and guide particles. Plasma waves move through the environment. Streams that will later pass Earth begin as conditions close to the corona. Parker enters that inner region and records the details before distance has smoothed them. The mission has also helped reveal switchbacks, sudden bends or reversals in the magnetic field embedded in the solar wind. These features had been detected before, but Parker found them more commonly near the Sun, showing that they are closely connected to the young solar wind. A magnetic field line that seems to fold back on itself is not a visible chord in space, but instruments can detect the change in field direction. Such measurements help scientists understand how turbulent and structured the wind is near its source. All of this is central solar science. It matters for the question of how the Sun fills space with plasma. It matters for space weather. It matters for the physical connection between corona and heliosphere. Yet it is not the same as viewing the Sun from above or below. Parker is close to the source, but its path does not climb over the poles in the way needed for direct polar imaging or high-latitude mapping. Its strength is depth of approach, not polar angle. This distinction can feel counterintuitive because ordinary thinking often treats closeness as the highest form of knowledge. If one person looks at a mountain from far away and another stands on its slope, the second seems to know it better. but a slope does not show every side of the mountain. A person standing close to one face may miss the shape that appears only from a distance or from above. The sun has a similar problem, except the mountain is plasma. The slopes are magnetic, and the viewing angles are governed by orbital mechanics. Solar Orbiter, by contrast, was built to increase viewing angle as well as approach the sun. It does not come as close as Parker, but it gradually raises its inclination through Venus flybys, allowing the poles to be seen from outside the usual ecliptic perspective. Ulysses earlier did not image the solar surface in detail, but it moved through high solar latitudes and measured the heliosphere above and below the sun. Parker sits between neither mission. It answers a separate class of questions, closer to the solar atmosphere's inner workings. A close equatorial path can still teach much about regions that eventually affect the whole heliosphere. The solar wind Parker samples near the sun may later expand outward and become part of the broader flow through which planets move. Disturbances measured near their origin may help explain changes seen farther away. Coronal structures imaged by WHISPER can be connected to measurements from other spacecraft. Parker's data become more powerful when combined with observations from Solar Orbiter, Earth-based observatories, and missions farther out. This is one of the quiet developments of modern heliophysics. No single viewpoint is enough. A near-Sun spacecraft sees young solar wind. A high-latitude spacecraft sees the Sun's polar environment. An observatory near Earth watches the solar disk continuously. A distant probe measures the outer boundary of solar influence. Together, they turn the sun from a flat image into a connected system. Each mission supplies a missing angle, distance, or type of measurement. Parker's orbit also shows how mission design carries scientific priority. To get extremely close to the sun, the spacecraft must shed much of Earth's orbital energy. Venus flybys help reshape the orbit inward. The result is a path optimized for close solar passes, not for rising steeply above the ecliptic. Every spacecraft is an answer to one set of constraints. Parker's answer is to survive near the sun and measure the inner heliosphere. Solar Orbiter's answer is to build a tilted view. Ulysses' answer was to use Jupiter to escape the flat plane. Near its closest approaches, Parker moves so rapidly around the sun that the environment changes quickly. Instruments must gather data while the spacecraft passes through intense conditions. The shield must stay pointed with precision. The spacecraft's autonomy matters because signals take time and because human controllers cannot manage every detail in real time. The mission is intimate with the sun but not casual. Its closeness is engineered second by second through orientation, shielding, and orbital timing. From that nearness, Parker has entered regions where the solar wind is still magnetically connected to the corona in ways that differ from conditions farther out. Scientists look for the Alvin surface, a boundary-like region where the solar wind becomes faster than certain magnetic waves can travel back toward the sun. Crossing such regions helps identify where the wind stops being strongly tied to the solar surface and becomes a more independent outward stream. This is a local physical boundary inside the larger story of solar wind formation. But even this deep access remains mostly near the sun's lower latitude environment. The poles still require another view. Their magnetic fields, coronal holes, and role in the solar cycle cannot be fully reconstructed from close equatorial passes alone. Parker can help explain the physics of the wind. It cannot by itself map the polar source regions from above. The question of what lies directly above and below the sun remains partly a question of latitude. This is not a limitation in the sense of failure. It is the nature of exploration. A mission designed for one kind of discovery leaves another kind for a different path. Parker's solar probe has brought science close to the sun's corona. It has measured plasma and fields where earlier spacecraft could not survive. It has shown that the young solar wind is structured, variable, and magnetically rich. These are deep answers, but they are not the whole answer. For the original question, Parker teaches a useful restraint. Directly above and below the sun cannot be found only by approaching the sun's surface. They must be found by defining direction, leaving the ecliptic, measuring high latitude wind, and seeing polar regions from better angles. Distance inward and latitude upward are different forms of access. A spacecraft may approach the sun's edge and still not see what sits over the pole. The missions therefore fit together like separate cuts through one vast structure. Parker cuts inward toward the young wind and corona. Ulysses cut upward and downward through the heliosphere. Solar Orbiter cuts diagonally, joining remote images with local measurements while its orbit slowly tilts. Voyager cut outward toward the edge of the sun's domain. The sun becomes more complete only when all these cuts are held together. Above the sun, below the sun, near the sun, far from the sun. Each phrase names a different scientific route. Parker's route is the one that asks how close a spacecraft can go and what the solar wind is like before it has traveled far. It shows that the sun's influence begins in complex magnetic motion near the star. The next step is to gather these roots into one answer, where the sun is no longer a flat disk or a single bright center, but a three-dimensional body surrounded by an atmosphere that keeps moving outward. Chapter 12: A Three-Dimensional Sun. The answer to what sits directly above and below the sun is not a single object. It is not a hidden planet balanced over the North Pole, not a matching body beneath the south, and not a secret layer of space waiting like a ceiling above the star. The answer is a set of directions that become real only after a frame is chosen. Above the ecliptic means one thing. Above the solar equator means another. Above the solar North Pole means something more physical still, because there the sun's rotation, magnetism, corona, and wind all meet. The first mistake is to imagine the sun as a flat face. Most images encourage that habit. The sun appears as a disk, with spots and bright regions spread across it. Loops rise near the edge, coronal holes darken in ultraviolet light, and active regions cross from one side to the other as the star turns. But the disk is only the side of a sphere seen from a particular direction. The sun has depth, curvature, hidden latitudes, and poles that are not placed for easy viewing from Earth. Once the sun is treated as a three-dimensional body, above and below begin to fill with structure. Near the solar North Pole, the surface and atmosphere may contain polar magnetic fields, high-latitude coronal holes, and open magnetic regions that allow plasma to flow outward. Near the solar South Pole, related structures appear with their own polarity and timing. These regions change as the solar cycle changes. They are not fixed caps. They are parts of a living magnetic system that turns, weakens, reverses, and begins again. The sun's rotation gives the poles their geometric meaning. Its magnetic field gives them their physical importance. At the equator and mid-latitudes, sunspots and active regions announce the cycle more visibly. Near the poles, the field can appear quieter, but carry information about what the next cycle may become. The remains of decaying active regions can be transported poleward over years, canceling and rebuilding the polar fields. In this way, the solar poles receive traces from lower latitudes and help prepare the sun's future magnetic pattern. Above the sun, in the solar north sense, the corona does not end abruptly. The atmosphere thins outward, magnetic fields extend, charged particles escape into space. Below the sun, in the solar south sense, a related outward passage continues. The word above may suggest stillness, as if something were suspended over the star, but the real region is full of motion. Plasma moves outward. Field lines curve with rotation. Particles travel through a vast environment too thin for ordinary senses and too structured to be called empty. Coronal holes are part of that answer. During certain phases of the solar cycle, especially near solar minimum, large polar coronal holes can dominate the high latitudes. In extreme ultraviolet and X-ray images, they appear darker than surrounding regions because their plasma conditions differ and their magnetic fields are more open. From these open regions, fast solar wind can flow outward into high latitude space. Above and below the sun, the star's atmosphere becomes a stream. Ulysses measured that stream by moving through it. Its high inclination orbit carried it over the sun's polar regions and through the heliosphere far from the usual planetary plane. It did not give detailed pictures of the solar poles, but it sampled the space shaped by them. During solar minimum, it found fast, steadier wind at high latitudes, distinct from the slower and more variable wind often measured near the ecliptic. That discovery helped turn above and below from map words into measured plasma conditions. Solar Orbiter added another part of the answer by changing the angle of sight. Rather than only remaining near Earth's plane, it used planetary flybys to gradually tilt its orbit and look at the sun from outside the usual viewpoint. Its early high-angle views of the South Pole began to reduce the old compression that made polar regions difficult to observe from near the ecliptic. A modest tilt could matter greatly because the old view had been so flat for so long. Parker's solar probe gave a different lesson. It showed that nearness is not the same as polar perspective. A spacecraft can travel very close to the sun, enter regions of the corona, measure young solar wind, and still not see directly over the poles. Its path answers questions about the inner solar atmosphere and the birth of the wind. Solar Orbiter and Ulysses answer questions about latitude and three-dimensional structure. The sun requires all these approaches because it is not one problem arranged in one direction. At larger scale, the regions above and below the sun continue into the heliosphere. The solar wind does not stop after it leaves the corona. It travels outward, carrying magnetic field through interplanetary space and shaping the region that surrounds the planets. Above the ecliptic, below it, north of the solar equator, south of it, the sun's influence fills a volume rather than a sheet. The heliosphere is the largest form of the sun's extended presence. This volume is thin, but it is not vacant. Charged particles move through it. Magnetic fields curve through it. The heliospheric current sheet divides regions of opposite magnetic polarity as it extends outward from the rotating sun. Cosmic rays entering from beyond the solar system are affected by it. Dust grains pass through it. Spacecraft cross it by measurement, not by sight, recording fields, particles, speeds, densities, and changing directions. What sits above and below the sun is partly this enormous structured environment. The ecliptic remains useful, but it can no longer be mistaken for the whole solar system. It is the broad plane in which Earth moves and near which the major planets travel. It is the reason so many early observations and missions shared the same flattened viewpoint. But the sun's own body is tilted relative to that plane. Its poles point away from the easy line of sight. Its wind fills space above and below the planets. Its magnetic field belongs to a sphere and a volume, not only to a disk. The original question therefore separates into several answers. Above the sun, relative to Earth's orbital plane, lies the northern side of the ecliptic, filled with interplanetary space and the sun's extended influence. Below it lies the southern side. Above the sun, relative to its own rotation, lies the solar north polar region and the heliosphere beyond it. Below lies the solar south polar region and its outward continuation. In both directions, the answer is not empty space alone, but solar atmosphere carried outward into a magnetic environment. A person could ask whether anything sits exactly on the line of the sun's rotation axis, extending from pole to pole into space. Along such a line, no known planet waits. No ordinary object marks the direction, but physical conditions still exist there. At different distances, that direction may pass through corona, solar wind, magnetic structures, energetic particles, dust, and eventually the outer reaches of the heliosphere. The absence of a single object does not mean the absence of content. This is one of the quiet turns in the question. The imagination asks for a thing. Science returns a system. It gives planes, axes, fields, flows, cycles, instruments, and spacecraft paths. It says that direction in space is not inherited from the body standing on Earth. It has to be defined. Once defined, it becomes measurable. Once measured, it reveals that the regions above and below the sun are part of the same active star that lights the planets from the center. Solar north and solar south are also not mirror copies. Their broad roles may correspond, but the sun's hemispheres can behave differently. One side may reverse magnetic polarity before the other. One hemisphere may carry more activity during part of a cycle. Polar fields can strengthen, weaken, or reorganize unevenly. A three-dimensional sun is not only a sphere instead of a disk. It is a body with asymmetry, timing, and memory. Future polar observations matter for that reason. As solar orbiter gains higher inclination, it should provide better views of the polar regions and improve measurements of magnetic fields that have long been difficult to observe from Earth's line of sight. Better polar knowledge can feed models of the solar dynamo, clarify the sources of fast solar wind, and improve understanding of how the next cycle forms. The poles are not remote corners of the sun. They are part of its larger magnetic engine. There is also a practical reason to care. The sun's magnetic activity affects space weather. Disturbances from the sun can affect satellites, radio communication, navigation signals, power systems, and spacecraft beyond Earth's protective atmosphere. The polar fields do not explain every solar storm directly, but they help describe the global state of the sun. A fuller map of the poles means a fuller map of the star that shapes the space around Earth. By now, the simple vertical language has changed. Above and below no longer mean what they meant at the beginning. They no longer come from a person standing on the ground and looking toward the sky. They come from planes and axes, from the ecliptic and the solar equator, from spacecraft paths and magnetic measurements. The question has moved away from ordinary direction and into heliophysics. Yet it has not lost its simplicity. It still asks where the sun's unseen sides lead. They lead first to polar regions, then to open fields and coronal holes, then to fast solar wind, then to the heliosphere, where the sun's influence spreads far beyond the visible star. The path outward is continuous. No sharp edge separates the bright disk from the wider solar environment. Layer by layer, the sun becomes less like a lamp in empty space and more like the source of a vast, moving domain. From far away, the star still looks simple, a bright point, a disk, a daily presence, but its surroundings are shaped in all directions, including those human beings rarely see. Above the sun, the magnetic field reaches outward. Below it, the same larger system continues. The planets move through one familiar slice, while the rest of the volume extends beyond that slice, quieter in diagrams but not absent in nature. The final answer is therefore patient rather than sensational. Directly above and below the sun, there is no cosmic ceiling, no hidden floor, and no single object that completes the mystery. There are the sun's poles, its high-latitude atmosphere, its open magnetic regions, its streams of plasma, and its heliosphere stretching outward through interplanetary space. The words above and below were borrowed from Earth, but once carried into space and corrected by science, they point toward a real and measurable structure. And beyond the last neat boundary of the question, the process continues. The sun turns. Its magnetic fields alter slowly across the cycle. Charged particles move outward through the corona and into the solar wind. The heliosphere holds its shape against the surrounding interstellar medium, not as a wall, but as a continuing balance. Above the ecliptic and below it, north of the solar equator and south of it, the star keeps filling space with the faint extension of itself. Farther from the sun, the wind grows thinner. The magnetic field weakens with distance, but remains part of the moving plasma. Particles from beyond the solar system meet the sun's outward flow. Dust grains cross quiet paths through the same region. Spacecraft, when they pass through these distances, do not find a final line drawn for the eye. They find changes in speed, pressure, field direction, and particle counts, each one another sign that the sun's presence fades gradually rather than ending at once. The question began with a childlike shape, one thing above and one thing below. It ends with a star understood as a volume-making body. The sun does not only shine into space, it organizes space around itself. Its poles are not decorative endpoints, and its equator is not the only meaningful belt. From every latitude, something leaves, curves, changes, and continues. The journey is complete. Rest well.